of Earth observations for water quality analyses as well. So that is just a little bit of my background, a little bit of the structure of the program. The program has been emailed out and is available to you. Today, we start with the introductory component from myself and some readings that I'm going to give you after the session. And thereafter, we're going to join in again tomorrow in a live session at 10 o'clock, where we look at the applications of the Google Earth Engine platform as a cloud-based computing tool that we can use to download our data sets and analyze data in a more structured and a bit more, I would say, user-friendly manner. And you'll see during this presentation, I'll bring up some of the pointers that we found during the research that we've done as to exactly, what are some of the limitations of using remote sensing data sets and what are some of the problems, etc. So on your screen, you will see the WaterNest online course, the learning material will be put in here, and you will get little notifications as well. So I hope that you all have registered. If you register, you have to register so that you're able to access the information and you're able to get all the notifications. So please ensure that you register. I think Dr. Kuchinga is going to put up that registration link onto the chat box in this session. All right, so that's the course, and that's the internet site that you will access to access information. So let's move on to some of the background readings that I want to start with. I just want to, sorry, I'm just looking for. Okay, so. All right, so I will upload some background readings for you to gain some information, and I will refer to those readings during the presentation. So let us kick off. The title of my presentation is The Role of Earth Observation for Hydrological Analysis, and it will be specifically for the case studies that I'm going to be talking about are based on work that we've done in South Africa and the Nkomati catchment. However, the context of the review that we did was for most of Africa. All right, so a little bit of an overview. I'm going to start off with an introduction. Where are we in terms of using Earth observation for hydrological analysis? What are space-based assets? A little bit of information about remotely sensed rainfall, evaporation, soil moisture, and how we use Earth observation data sets in these instances. What are the commonly used products that are available? Some of the challenges that we have working with remote sensing data sets, and a brief information session on the application of remote sensing rainfall, for example, in the Kaap catchment, which is based in the Nkomati catchment in South Africa. And that's basically what we're going to talk about this morning. All right, so the demand for water is growing inexorably, and this is highly due to population growth and its impacts on food production, urbanization, climate change and variability, and various other factors. So there's so much of pressure and demand on water, and water is vital. We all know that. We need it for life itself. We need it for drinking. We need it for ecology, agriculture, energy, for industry, for sanitation. And especially, for example, here in South Africa, over the past 5 to 6 years, we've really seen the impacts of climate change on our water resources, on our rainfall, the variability of rainfall, the changes in rainfall between the different provinces, the different areas. We've got summer rainfall regions, winter rainfall regions, and we've seen drastic changes in our rainfall patterns during these times, as predicted by the climate change specialists. And this has resulted on lots of pressure on our water resources systems, on agriculture, excessive, droughts. We've had day zero in Cape Town, where people were without water. At the moment in the Eastern Cape in South Africa, people are really battling without water. Dams are low, agriculture is suffering, and in South Africa, agriculture is probably the biggest user of our water resources, and and we need that in order to ensure food security and food productions. So water is of utmost importance, and there's a lot of pressure on the hydrological community, on people involved in water resources studies and management, and policymakers, decision makers, to adequately plan, to manage, to be able to predict the changes in water resources. So there's a lot of pressure on the hydrological communities to make these water resources management decisions. However, these decisions don't come with a thumbsuck, and these decisions require adequate modeling and information. They require prediction. They require vast amount of data, both as input and validation and calibration. So in order to make adequate decisions, we require data. And that data has to be both of good quality and good quantity. So the quality of the data refers to error-free data, and the quantity of the data refers to the lengths of the data sets, the spatial coverages, the ability for that data to be used adequately to make the decisions. And it must be the right data sets. You can't just use any type of data for any type of decision-making system. It has to be the correct data. It has to be validated data. And data collection in itself is becoming more difficult. And I have put out some readings about the state of, data collection and measurement in Africa, and some documents by the World Meteorological Organization as well, about the status of water resources and data availability, data management, monitoring networks, etc., and the decline in these monitoring networks. So data collection is becoming more difficult. And throughout Africa, we can see that this is mostly due to the financial constraints. It takes a lot of money to maintain the systems, to build the systems, first of all, and then to maintain these systems adequately. It requires human resources with the appropriate skills to be able to analyze the data sets and ensure that they are, the appropriate quality, so that we can make good use of these data sets to make our decisions. And the accessibility. So being able to access our monitoring networks and being able to place our monitoring networks at points in the catchment where we require that information is of utmost importance. Data accessibility also refers to custodians. So there are many custodians of data where people are doing monitoring and measurement, etc., or entities are doing this, and they're holding that data and expecting payments for that data set. And another and final problem, especially in South Africa, is the security issues. So apart from the fact that the monitoring networks and systems are exposed to climate hazards, to storms, and, to natural disasters and destruction, lightning strikes, for example, they're also prone to theft. And a lot of the time, the metal from the instruments are stolen so that people can sell the metals and make money out of it, or the batteries are stolen, and that system then loses a whole range of data, loses quality, etc. So this is another important factor that's influencing or impacting the data collection. So in essence, data collection is becoming more and more difficult for us. So this is where Earth observation comes into play. And, you know, here we have Earth observation where we're gathering information about planet Earth, both physical, chemical, biological systems, via remote sensing technologies, supplemented by sorry, just a sec. Supplemented by Earth surveying techniques encompassing the collection, analysis, and presentation of data. So we have these satellite technologies, remote sensing technologies, which are up there in space, and we have the ability to use these technologies now to further enhance our data and monitoring networks, and to actually give us another opportunity for a data input. So Earth observation technologies such as satellite-based monitoring can be very useful as they provide a cost-effective means of replacing or complementing field data collection. Now, that's a very important point because for one, it's a cost-effective means in that the satellite's been put up there and there is no, you know, it's just a matter of being able to log into the networks that produce these systems, etc. Most of the time, these satellites are backed up by huge projects, you know, and huge entities like the European Space Agency, NASA, for example, JAXA, for example. And so they are backed up by huge facilities, and the data is, you know, the beauty of this type of data set is most of the time the data is freely available or made, or components of the data are transformed and made freely available, especially to us in Africa, where, you know, we really rely on these free data sets to make the decisions and to use the information adequately. So some of the main benefits of Earth observation data is that they can provide a large coverage, an area, and especially remote areas. If you think about the mountainous areas where we can't go up and put a rain gauge, we're able to actually access information at these areas with remote sensing data sets. We're able to get systematic, repetitive data captures. And that's important. And that means we have a data set where we have, you know, a specific spatial coverage and a specific temporal coverage. So a special resolution or different resolutions available to us, but also different temporal resolutions available to us. So some of the data sets can be available weekly, monthly, some of them available daily, and even sub-daily data sets available. And we require different temporal resolutions for different tasks. So Earth observation data can be integrated with our field or our remotely collected data, real-time data sets, etc., to produce effective and up-to-date predictive and analytical products. So we can use the Earth observation data sets in an effective way so that we're able to enhance the actual data that we have. Don't get me wrong, there is definitely still a need for the physical in situ measurement systems. There's no doubt that physical in situ measurement systems are still required. And they are required in order to actually validate and calibrate our models, but especially to validate our remote sensing data sets. And more and more, we find that the remote sensing data sets or Earth observation data sets are integrated or blended with the actual measurements and other modeled data that's available to us. So as we can see, Earth observation data then becomes a very important component to adding to the declining networks and giving us an information product that we can use to make our hydrological decisions. Several research studies have assessed the potential or the actual use of satellite-based Earth observations in hydrology. And, you know, there are so many review papers that are written where people have reviewed the use of Earth observations, multispectral, hyperspectral data sets, etc., for hydrological analysis and studies. And a lot of these have been made towards developing or modifying approaches to estimating the different fluxes. So estimating rainfall, evaporation, soil moisture, or state variables for that matter. Variables such as land surface temperature, runoff, snow cover, water quality variables, elevation information, land cover information, surface roughness are just some of those variables that can be estimated from remotely sensed data. And these variables then can be further either modeled, put into algorithms, or put into hydrological models to help us to get our predictive analyses going. So important fluxes such as ET, soil moisture, precipitation, all of these can be estimated from Earth observation data sets, and we can work with these and incorporate them into models to make up water budgets. We can link all the spatially derived estimates into our hydrological models and improve the hydrological modeling components where we are in normal circumstances, we wouldn't have had that data because we don't have the monitoring, in situ monitoring networks. And therefore, Earth observation data sets have become extremely vital in adding value to these decision-making systems. So a little bit about remote sensing orbits, the electromagnetic spectrum. I'm sure many of you who've joined this course have some basic understanding of what remote sensing and Earth observations are. Basically, remote sensing is the acquiring of information from a distance. And here I've got the Earth Data NASA learning platform, which gives you some information on what remote sensing is, what sensors do, what are the orbits, what is the meaning of resolution, what is data analysis interpretation types, etc. So I would advise you to go to this website if you want some basic information on what remote sensing is and how we use this in order to get our spectral signatures or our spectral analyses and to produce the maps that we need in order to get our data sets. So please take note of that site. And, over the past 30 years or so, when satellites first started with observing the planet, there were just a few of them that were up there, and I think the Rainfall one was TRIM 1987. That was the real kickstart of monitoring the planet, in terms of its Earth sciences or Earth parameters, and especially those related to hydrology. And in 2009, the Group on Earth Observations produced the space-based assets diagram or picture illustration of the different satellites that were available in space and data sets that were available from these. And you can see here there's about 3, 6, 9, 12, 13, 14, about 15 different options, driven a lot by the United States. There's the Meteosat, EU Metsat, European Space Agency. There's some there, the China and India. JAXA, the Japanese space agency as well, joined up a lot with the the United States with NASA, and they produced the TRIM product actually. So that's the TRIM Rainfall product. And yeah, so there were about 15, 16 observational satellites looking at earth sciences, earth-related parameters for earth sciences related work. If we look at 2020 and beyond, you can see that these numbers have drastically increased, and we're sitting at more than 25 different types of operational satellites, many of which have already been replaced after various missions. For example, Landsat here, we can see it's already Landsat 7, 8. There's Sentinel-3 out there with EUMETSAT. There's Landsat 8 there. You can see there's the Sentinel ranges. Landsat 9 is already up and coming as well for 2020. There's different ones that started up in 2022 as well. And there are also many of what we call CubeSats that are launched. So CubeSats are very small satellites built with specific sensors and specific cameras on them, so that there's specific information that's captured. And a lot of them can be either multispectral or high resolution hyperspectral CubeSats that are available. So the entire space-based assets is changing, and space-based information has become more and more accessible and available to us. And is definitely on the increase. And yeah, recently I attended the South African National Space Agency Symposium, which was held with NEOS, which is the National Earth Observation Space Secretariat for South Africa. And there were lots and lots of discussions around, opportunities for space-based technology and its use to all of us in gaining a common ground, and us realizing that we need to, take this technology and move on with it, and look forward to using this type of technology into the future. So here's a bit of a review study that was done on the use of Earth observation in water resources management, and in particular, some of the contexts of research that we came across were specific studies relating to land cover, land use mapping. Remote sensing Earth observation technologies plays a huge role in mapping our different land covers and land use. And for example, in South Africa, we have various national land cover databases that are updated every 3 to 5 years with, the latest available technology and remote sensing data sets. There's been a lot of work with earth observation and irrigation and water use efficiency, crop water use in particular, lots and lots of work being done with crop water use, and, understanding the how much of water crops use, so that we can model that, so we can schedule irrigation, so that we can predict, whether this crop is worth growing in a specific area, etc. Slope stability mapping, DEMs. I mean, there's no doubt that Earth observation satellite imagery plays a huge role in mapping out areas. More importantly, recently, flood risk mapping, but also floods and droughts mapping, very important component. Water quality monitoring, pollution source detection, wetland extent mapping, snow extent mapping, water footprints, water accounting, newer avenues of water accounting, and estimating, the water footprints, hydrological modeling, in particular, estimating parameters for hydrological models, and replacing the in-situ measurements with the Earth observation data sets. Estimation of drought indices, another important area of interest and research for water resources management, and that these studies are throughout the world, but there are studies that are being done in Southern Africa as well. These are just some examples of how we, get our satellite rainfall. So this is an example of a TRIM data set image for a basin in China. And from this diagram, we can see that the satellite rainfall, which is the TRIM-based rainfall, has been mapped here. And we can see from this diagram, or this illustration, sorry, that there's a very distinct change in the rainfall. So we can see, if we look on the right-hand side map here, we can see everything in the greenish region is between 500 and 1,200. And we can see how nicely that's picked up here by the satellite information. And that transition area, the blue area, is these lighter areas here. And then as we go here into these drier regions, the shades of gray are able to pick up. So if we compare these two maps, we can see that based on the rainfall data set, the TRIM data set is following the trend and is able to pick up the high and low rainfall. So this is just an example of a remotely sensed rainfall product that's available, and this is the TRIM product. In the same way, we can get soil moisture. So this is an example of soil moisture from thermal data. And, we can get different soil moisture information. We can get soil water indices, etc. as well. And this is an example from thermal data, thermal imagery over a specific area. Land cover mapping, this is an example of the different land cover mapping or that's available to us. I mean, these are just some older examples for illustration purposes, but here we've got Landsat at 30 meters, Modus at 250 meters, and QuickBird at 1 meter. And we can see the differences in the resolutions, Modus being a coarse resolution, 250 meters, Landsat at 30 meters, finer resolution, we're able to pick up finer details. For example, if we look here on the left-hand side of this map, here we can see there's something going on. It's not too clear. Here on the left-hand side in the Landsat image, we can see a very defined, clear circle, and that tells us there's some irrigation going on here, particularly pivot type of systems that give us this definite pattern. And obviously, QuickBird at 1 meter resolution is giving us excellent detailed information from our Earth observation data. This is an example of drought monitoring. So, just distinguishing the wet and dry regions. This is how we could use Earth observation for drought monitoring and mapping. So there are many, many opportunities for the use of Earth observation data for water resources management in South Africa, in Southern Africa. We just have to grab the opportunities and make best use of the potentials that are available to us. There's a lot of research. There are hundreds of papers. There's so much of research that shows the potential for Earth observation water resources management. But from what I see, there are limited studies and there's limited uptake to utilizing this information. And its full potential is limited both internationally and in South Africa. And I think in the international market, there's just a greater push towards using the data. The main fact being that the data sets are freely available. There's, improved technologies for accessing the data sets, etc. In Southern Africa, we're finding that there are certain groups of people that are pushing it, and there are certain groups that are willing to engage. However, there's greater reluctance. And for example, as much as in academia and in research, people are trying to move towards this direction, it's going to be more difficult for consultants and actual practitioners to pick up these technologies and move forward with them, particularly in instances where the data sets are not freely available and we're heavily reliant on paying, for example, SOARs and other institutions for data. The other very, very important aspect to consider is that remote sensing and Earth observation data sets are are data intensive. So they require large bandwidths. They require a lot of computing power for the computers to run that model. However, to match that, there's so much of improvements in our computing technologies, and we sitting with i7s as desktops, etc. And that's more than enough to start engaging with this type of work. Data storage capacities. Lots of information gets produced from these. And I think the cloud-based computing systems now are providing us better opportunities to deal with these storage capacities, etc. But I think for me, from what I find is the biggest challenge for using Earth observation for water resources management is the skills required. People shy away from using remote sensing satellite. They hear the word satellite data and they think, oh my goodness, this is going to be so difficult, etc. So the appropriate training is required, the appropriate skills is required, appropriate human capacity development is required if we're really going to push for the use of Earth observation for hydrological analysis to really, really move forward. And here at the bottom, I've got this little a diagram from Van Dijk and Zulu, I think it was their paper in 2011, that showed the different components, how we could use satellite ET, for example, satellite products in the various components of modeling for water resources management. I want to take a quick break, if I can just have a 5-minute break. And give you a chance to load any questions, please. Can we have a 5-minute break? And we can load up any questions so far on the review components. Any thoughts you would like to share, anything that you'd like to put, please place that onto the chat. And we'll take a 5-minute break. We will resume at 10:50. If you could just post your questions on the chat in the meantime, before we move on to the next section, which is looking at specific products for remote sensing, Earth observation, and for hydrological fluxes. Thank you.
Thank you, Chetty. We have put the registration link in the chat. Could we please all register? I'm going to repost it now. Thank you.
start up again. Just a reminder, the link is now working, so can we please ask everybody to register on that link? If you have any issues, just post your issues also on the chat, and our administration will pick that up and try and resolve it. All right, so we move on to some of the commonly used and available Earth observation or remotely sensed products that are available to us for use in hydrological analysis. And remember, these products we're looking at are in particular for hydrological analysis. And I've selected 3 that I'm going to talk about, well, 3 areas that I'm going to talk about, but there are many, many other different, products that are available and different components that are available that can be used in various hydrological models and applications. The first one I'm going to talk about is rainfall, and there are many satellite rainfall products that have been made available, and I'm going to review a few of them, a few commonly used ones. I'm going to start off with the TRIM Tropical Rainfall Measuring Mission, which was launched in about 1997. And I think this is a big one because it earned many, many huge research breakthroughs and really laid the foundation for the future of rainfall and Earth observation or precipitation Earth observation and the different types of algorithms and opportunities that have become available. So this really laid the grounding work for that. So the precipitation radar, passive microwave, and visible infrared scanner available on the TRIM platform. The TRIM data set was also merged with the Global Precipitation Climatology, the GPCC rain gauge data set, and using the actual Earth observation satellite remotely sensed rainfall information together with the GPCC data sets, various products were produced at different temporal resolutions. And the most commonly one is the 3B42RT with its optimized algorithms. And this is where the rainfall products, satellite Earth observation data set merged with the global precipitation data sets in a specific combination of rules where slight corrections took place in optimized algorithms, and that's how the various products became available. And most commonly used, I would say, is the 3B42RT version of TRIM. Subsequent to that, TRIM, fell away in about 2020, I would think officially. GPM was launched in 2014, and this was the sort of successor to the TRIM network to provide the next generation global data sets for both precipitation, well, that includes rainfall and snow. GPM was launched in 2014, and I think there was another launch of different sensors in around 2019, and it was building on the successes of the TRIM mission. What's happened now is a lot of the intermittent, so the in-between times from 2014 through to 2020 gave us some new combined data sets of TRIM and GPM that have become available. And I think there is a continual update of the TRIM / GPM data sets that is occurring. So this is one to look out for if you're interested in using satellite-based rainfall or precipitation data sets. The TRIM / GPM data set is probably the longest running and updated, one of the longest running and updated data sets that are available. GPM, again, was initiated by NASA and the JAXA, that's the Japanese Aerospace Agency. It's also had different partners within its system, the International Space Research Organization, it's had the Indian Space Organization, NOAA's been involved in it as well. So there are various partners playing their role in taking forward the GPM missions. And we move on. So this is an example or an illustration of what the GPM sensors look like, or the satellite looks like. It's got microwave images. It's got precipitation radar at different bands, 13.6 and 35.5 gigahertz bands. It has a range of resolutions, 250 to 500 in some instances. And the different sensors measure at different bandwidths as well. So there have been improvements. For example, there have been changes in some of the spatial resolutions, but the sensors are set and we can then take that information. I think the algorithms then take that information and adapt it to give us our defined products for specific spatial and temporal resolutions. Another example of a global precipitation data set is the Imerge Data Set. Also about 20 years of data available. The Imerge algorithm combines information from a constellation of satellites operating in the Earth at any given time for precipitation estimation over the Earth's surface. It's an extremely valuable tool, and the Imerge is, it's seen as one of the emerging technologies that are based on algorithm and what we call reanalysis products as well. The version 6 of Imerge has been released, and this algorithm can fuse early precipitation estimates collected between 2000 and 2014, the year 2000 and 2014 during TRIM, as well as the GPM satellites information. So the Imerge product is quite an important product to consider. The next one is the Fuse RFE. So there's the Fuse RFE and the Fuse ARC that are available. The Fuse RFE is also hosted by NOAA and operated since 2001. It is a very highly recommended product. There's a lot of work gone into its reduction in errors, improved accuracy, speed, portability, etc. It's got a special microwave imager, advanced microwave sounding unit, combined with GTS rain gauge data and a GPI and infrared temperature as well. So it's a very important product that's been widely used, tested, and algorithms are continuously being improved. That's the Fuse RFE, and it is available on a daily data set, at a daily temporal resolution as well. The other product is the Fuse ARC2, created in 2005. And it optimizes the Fuse RFE. So it's an optimized version of the Fuse RFE. That's the Fuse ARC, and it's available on FuseNet. It is freely available for people to use, and it's specific to Southern Africa. So this is a good one if you want to use information for Southern Africa. It also has a sub-daily data set available to it, which makes it very important for use. Another one is the NOAA's CMORPH product, which was launched in 2002. And CMORPH also very widely used for a variety of applications, and it's quite a flexible method using microwave satellite sources, etc., and available on a daily time state. And the last one I'm going to talk about is TAMSAT. And TAMSAT is the tropical application of meteorology using satellite data and ground-based observations. And this one is based at the University of Reading, and where a daily rainfall estimate for all of Africa produced at 4-kilometer resolution. The archive spans 1983 to 2021, so it's a nice long data set that's available, which makes it very suitable for flood risk mapping, for long-term predictions, etc. And it's widely used in early warning systems, drought applications, agricultural decision support systems, etc. Also, the data set is available for other areas, and a lot of the developing countries are looking at the TAMSAT data set for use in its application as well. This is an example of a TAMSAT produced image for Africa. For a particular month. So this is November, Pentad 2. That's the way in which they estimate, they separate their products into pentads. And if you want to read up more on that, you can just Google TAMSAT and you'll be able to get to their page, and all the documentation related to TAMSAT is available to you. So these are just some of the examples of the satellites that are used for rainfall products in particular. There are many of them, and I think most commonly, as we've spoken about, is the GPM, TRIM GPM data sets that we've spoke about. The ones that I've reviewed are just those that are commonly used in hydrological application research studies. There are many other available products and reanalysis products as well that are available, where reanalysis products are rainfall products that use satellite information, gauge data. They then put through algorithms and they are corrected, either bias corrections through specific statistical techniques, and then a data set is produced. And that is something also that's gaining a lot of momentum and research, is the reanalysis products that are available. All right, there's lots and lots of case studies. I'm not going to go into details here, but you can read up on all of the evaluations of the different products that are available. And, depending on what you're using them for, you may find one of those products suitable for the type of work that you're wanting to do. The next thing I'm going to talk about is remote sensing and earth observations for evapotranspiration estimation. And this is a big one as well, because a lot of work is done in crop water use, irrigation scheduling, agricultural water use, agricultural suitability mapping, land use mapping, etc., where evaporation information is used. And to put up actual in situ measurement systems for actual evaporation on the ground is extremely costly. Systems like surface renewal, eddy covariance systems, etc., or if we're using, something more spatially derived like scintillometry, those costs hundreds and thousands of rands to put in systems, to maintain the systems, and to get out the data sets. And yes, they are invaluable to put up those systems. It's very important for us to use those systems for validation purposes. However, it's not practical to put it up everywhere, and a lot of those systems are placed dependent on where research is occurring. So lots and lots of work has gone towards using Earth observation data sets and our remotely sensed satellite products that are available to incorporate into evaporation estimation algorithms, so that we can use these remotely sensed data to input into evapotranspiration algorithms, so that we can estimate ETAs, for example. Some of the systems that are commonly used will be the metric system, CBAL, ET look, for example. These are all remotely sensed ET-derived estimates. There's EDTIs, evapotranspiration drought indices also. So there's various other satellite-based evapotranspiration indices that are used. And a common one that we're going to talk about in our context is the SEBS model. And this in particular is because the SEBS model is freely available on the IWRM platform, and it's extremely user-friendly, and you're able to actually take different types of satellite data sets and incorporate them into the SEBS system. Lots and lots of research has been done in terms of both in Southern Africa and internationally, in terms of incorporating different data sets into the SEBS model. For example, Modus, ASTER, MERIS data, Landsat data, modified Sentinel data more recently, in order to use this information into the ET-based algorithms. So the surface energy balance system, for example, is a GIS-based system, which is housed on the IWRM platform, which can ingest different variables that are derived from our satellite-based products. And ET-Look, for example, very widely used in the Netherlands by IRI-Watch and WaterWatch, for example. That's the group eLeaf that worked on the ET-Look work. Metric, also very commonly used. CBEL is linked to the ET-Look work. CBEL is probably the underlying model from ET-Look, and SEBS is closely related to the CBEL model as well. However, SEBS is freely available. CBEL comes with a cost associated. Modus, the Modus platform that's available, Modus has a large number of products, satellite-based products that are available online. And one of the Modus products that are available to us is the Modus ET data set. It's called Mod 16. And it's got a specific 8-day temporal resolution at 0.5 kilometer spatial resolution. It is a global product that's freely available, and work has stopped a little bit on Mod 16. There were talks of people looking at, continuing the research. The research that was done in that work needed to be continued, but funding stopped for it. But the last I heard was that work is continuing on the Mod 16 product now. So that is a freely available data set. This is an example of an ET-based, so we looked at this example for rainfall previously in the high basin. This is an example of how you would map actual evaporation across a catchment, and we can see that this is, I think, CBEL that was used to map ET here, and we can see how specific and how we can see the different gradients of ET being able to be mapped out from remotely sensed information. So it's giving us quite good information, and it's better than zero and better than not knowing and having a -999 missing data, etc. At various points. This, for example, is an illustration of how we would use our evapotranspiration algorithms. So, for example, SEBS or CBEL, in order to estimate our evapotranspiration of different crops in an area. And we can see from the imagery here that we can distinguish the different crops here. They're probably different stages of growth and the different ETA or evaporation coming off these different crops. And so, yes, we can map this quite easily, and it's very successful, a technology that's used for agricultural water use, for irrigation scheduling, etc. And there's lots and lots of research going into creating big systems, which put out information for stakeholders to use. This is just another example of a comparison between surface renewal, which is an actual in-situ measurement system, and Modus ET. And you can see that even though there's discrepancies in terms of, one is overestimating, one is compared to the observed data set here, there are many instances where the data is actually showing the exact same trends, where there's decreases seen in the observed and the simulated values as well. And a lot of the trends are still being followed. And, there could be various reasons as to why this is happening, and lots of research is going into understanding why there are discrepancies between our measurement systems and our model systems, and how we can minimize those discrepancies. The last thing I want to talk about is soil moisture measurement. And, if you think about it, understanding the soil moisture is quite a tricky task in itself, in that in order for us to understand soil moisture, we essentially have to know what's going on almost everywhere. That means we have to have lots and lots of points of measurement. And, we look at different types of TDR, watermark sensors, for example. Those are all the ground-based measurement techniques that's used to estimate soil moisture. And it's labor intensive. It requires lots of capital. It requires lots of time, and it's point-based measurements. And in many instances, we're modeling or making decisions at a catchment or a subcatchment scale. And therefore, more spatially derived information on soil moisture is important. And this is where remote sensing and land surface models come into place, in that they can then play a role in being able to estimate soil moisture at larger spatial scales instead of just point measurements. These are just some of the techniques that are used to measure soil moisture. Thermal infrared, gamma radiation, microwave radiation, very important active and passive sensors, very important aspects of sensors that are put onto our satellites in order to be, detecting soil moisture. Several active and passive microwave sensing products are available, and I think these ones have seen the most amount of advanced research. This is, for example, AMSRI, the AMSRI product, which is the Advanced Microwave Scanning Radiometer. The SMOS product, also very prominent product available for soil moisture estimation from Earth observation data sets. The ECV data, very, very important, based on climate variables as well. And more recently, SMAP and SMOPS and CCI. Those are the three most latest available techniques. SMAPs also very important in terms of the most updated soil moisture available. And soil moisture, spatially derived soil moisture estimates and estimates of soil moisture indices are extremely important, not only for agricultural use, agricultural water use, but also for flood risk mapping, for drought monitoring and mapping. Extremely, extremely important. So these are just some of the examples, AMSRI and SMOS. Those are the satellites that are up there. You can also use land surface models. I've got an example here, the PyTop copy. This was a model that was produced here in South Africa at the University of Natal in the SAG group. They looked at the PyTop copy model, which sort of worked off the Topkapi model, which is the Italian model, and used remote sensing information to estimate soil moisture at 3-hour intervals. And it was actually quite a wonderful product. Unfortunately, when the research stopped, the data set stopped along with it. So that was a nice product that could be used as a modeled product. The one important thing is that when we want to use data sets, we want to make sure that they're easily available for use. And I think one of the things about the SMOS data set, for example, it was not very user friendly. However, over time, And with more developing, especially with, you know, R and Python becoming available, people have been able to adapt it and make it more user-friendly. This is an example of Imerge data set. You can see there's lots of missing data here and there. And, you know, this is one of the factors we have to consider. And that is why the in-situ measurements are still so important in being able to fill in the gaps and to make up an improved data set. This is an example of the SMAP soil moisture data set that's available. It's a global product also at a 9-kilometer resolution. And this, for example, is a 3 days composite file. Lots of other opportunities available for remote sensing and earth observation data sets. We spoke about rainfall, evaporation, soil moisture. I started off telling you about land cover and land use mapping. And this is, for example, is Landsat, I think one of the biggest contributors for land cover and land use mapping since 1972. And Landsat's emerged. Landsat 9 is already being launched, or it was about to be launched in 2021. I can't remember whether that actually happened or not. But yeah, so there's lots and lots of you know, opportunities for Landsat to be used in any one of your types of Earth observation studies. Sentinel as well. You can see Sentinel also has been developed from Sentinel-1 right through to Sentinel-6, Sentinel-3 and 4 being the most, or Sentinel-5 and 6 being looking at different aspects, but Sentinel-3, the bigger picture, looking at a lot of the earth sciences types of variables that are available to us. So Sentinel, another one of those important components. So that brings us to the end of the different, you know, types of products that we could use for the various aspects of hydrological analysis. And I've just touched on, you know, a few of them. Depending on what you want to do and what your task requires, you may have to find different products or more specialized products, or you may have to find a product and modify it to make it applicable for what you're wanting to do. I want to end off today's session with a very quick overview of a small study that we did in the carp subcatchment. So the carp is a subcatchment of the Inkomati catchment in South Africa. So for those of you who know the Kruger National Park area, the Inkomati catchment lies in, you know, close to the Kruger National Park. And this was just a preliminary investigation in applying remotely sensed information and data sets to the ACRU model, the agro-hydrological model. This model was developed in South Africa for Southern African conditions at our university. And lots and lots of research has gone into modifying this model and making it a wonderful research and teaching tool. And a lot of my PhD research is going into incorporating and linking hydrological, this hydrological model to remotely sensed Earth observation data sets, and seeing how we can either blend products or use reanalysis products, or use satellite-derived Earth observation variables for different components of the model. In this instance, this case study looked at, in particular, the rainfall component. So I'm not going to go into detail too much about the ACRU model itself, but the model was configured according to land cover and soils information that was available. And the model works, you know, best if we break it up into HRUs, which are hydrological response units, so that we can derive a flow path for water that moves through the catchment. And we use the most updated land cover information database that was provided by the Inkomati Catchment Management Agency at that time. It was a land cover database that was generated from the 2010 high resolution spot satellite imagery at a 2.5 meter pixels, and it gave us quite detailed land cover and land use patterns in the catchment. So this is just an example of the land cover, and these are X23, X22, X23A. These are the different sub-catchments within the catchment. This is an example of the soils information, and this is an example of how we, modeled the catchment. So this was my HRU layout. So I had an HRU, it flowed into a dam flow node, into the dam, and then out of the dam. And my HRUs were made up of land cover and soils variations. I think the most important thing for us here was the rainfall. So what I did was I downloaded data, which was the actual in-situ rain gauge information from the ARC, that's the Agricultural Research Council database that was provided to us. And we had a short data set from 2006 to 2013 for that specific site. And we used the TRIM B342 version 7 daily rainfall estimate, which we downloaded from the TOVUS download data portal. And I think these days that entire analysis portal has become null and void unless you want to use it in particular. Now you can get the data directly out of the Google Earth engine. The images were processed in ViSat and converted to GeoTIFF, imported into ArcGIS 9. So there's a lot of processing once you get your actual satellite data set. That data trim image was laid over the CARP subcatchment according to the quinary images that were available to us, and pixel values were identified and recorded for each of the quinaries. From those pixel values, a daily time series of rainfall was set up and incorporated into the ACRU model. So ACRU generally will take in a rainfall file that is a time series file from a rain gauge. What we did was we produced a new rainfall file based on the satellite rainfall information. We also used the climate ET data from the ARC available data set in order to drive the model. So this is an example of the different pixels that were available across the subcatchment. And after running, if we compared the rain gauge and satellite rainfall, you can see that there were certain instances in which the satellite rainfall was underestimating the peaks of the rain gauge at that point in time. And that is a common issue that we have with certain satellite rainfall products where they sort of down the extreme events. However, we can see that there's a wonderful trend, a really excellent trend that's going on here, and it's quite a good close fit. Right, so that's the observed and simulated now here. After running the ACRU model, the simulated stream flow is our red lines, the observed stream flow is our blue lines here, and we can see again the simulated stream flow in certain instances slightly underestimated compared to the observed stream flow. And lots of research is going into looking at why these differences occur, especially in terms of peak discharges, for example. This was also quite a short period of study, so you need a much longer data set to actually look into these type of results. This is one event, for example, where we can see our R-scared is 0.5, almost 0.55. And there is this comparison between the observed and simulated stream flow. We can see the trends are matched quite nicely. Again, the observed peaks are higher than the simulated peaks. And we suspect that the peak discharge equation in the model itself also needs to have a better look at. So that was one other option for looking at more advanced studies in comparing our observed and simulated when it comes to incorporating our satellite information. This is a nice one. So this is where we compared the observed stream flow with the simulated or modeled information, and then the simulated using the satellite. And you'll see that the simulated using the rain gauge, we had huge discrepancies here. And if we compared the satellite and the model, we had a better fit in many of these instances. So again, it's a short time period. It's one event that we were looking at, and this requires much further research. But this shows a lot of hope in terms of what we can achieve. And, this is the way we're looking at now, is to improving, we'll be looking at creating new time series, looking at improving the comparisons between the satellite and the rain gauge information, possibly creating reanalysis products and blended products for a better understanding, and taking that forward into incorporating it into hydrological models for our analyses. Some of the challenges that we, had during this experience was taking in satellite information and plugging it into an operational hydrological model. Sounds appealing. However, it is a scarcely explored domain of research. So you can't just take your satellite information and plug it into your hydrological model. A lot of the time, there needs to be some sort of change in the model structure in terms of how the model takes that variable in, and not a lot of thought has gone into that in many instances. So it's not a very direct process of just replacing your ET value with a spatially derived ET value. A lot of the time you have to actually think out the actual ET process and use the appropriate pathways to ensure that you keep your hydrological logic intact in terms of your modeling strategies. The integration of satellite Earth observation products poses a significant challenge, in terms of directly using our data sets. And we have to accommodate spatial data sets in a particular way, and research needs to go into that. And I think this would be, different models would require different structural changes and methods of incorporating or ingesting these satellite-based data sets. There are also lots of challenges with working with remote sensing data sets in operational catchments, because there's so much of things going on in an operational catchment. You have to understand, you can't just simplify it and say, okay, there's only 3 HRUs and this is where it's going. You often have irrigation occurring, you have abstractions, you have to make sure that you're able to model the catchment appropriately and account for all the processes. I think a major challenge is access to remote sensing data sets. And, previously I remember there's lots of waiting periods, registration periods, etc. I think Google Earth Engine and cloud computing has really, really, taken a lot of those challenges away, and has made access to data much more improved. And the whole open source, using QGIS, using open source, putting it out there, people, you write a code and you put it out there, and you just say, I'm having this problem, and you'll find people from all over the world starting to contribute to what your problem, could actually be alluding to. Different frameworks, methods, tools, for example, if you're using TRIM, you must use TOVUS, or you must use a different system to actually download the data set. And then you have to use another system to analyze it. And then you have to convert it, etc. And that's time consuming. And again, I think the cloud-based platforms, particularly Google Earth Engine, has been able, it's a good way of minimizing all of those downtimes, I should say, and time-consuming tasks. Expertise required to manipulate, process imagery, prepare data as input into models. And I think this is something that I've seen being an educator and being in academia over the past 20 years or so. for me, I think there's a huge skills gap in terms of coding, people being able to actually do their own coding, learn the different types of machine languages so that they can incorporate the different technologies and actually adapt their models. And I think that's the biggest flaw of most of the earth sciences students had some type of coding knowledge and, basic programming skills that would make life so much easier in order for them to pick up programs and be able to use Python scripts, create their own Python scripts, pick up the other different languages to adapt the models and things like that. It would make life much more easier. Supercomputing facilities, I think, in certain instances where you are modeling large catchments or large areas, you do require lots of computing speed, particularly if you're working with models that are not lumped and they're distributed and they have various processes involved in them. It could take up lots of time, energy, space, and modeling power, computing power. And the last point that I've left is the availability of good quality data. Without observed data, without proper, appropriate lengths of good quality in situ data, our satellite information becomes null and void. We require it for validation, for calibration, so that we can use our Earth observation data sets with confidence and certain levels of uncertainty associated with it. So my preliminary investigations and lots of the research that we've looked at show great potential for Earth observation in hydrological modeling. Subsequent to this, we've modeled the Mgeni catchment and the Breede River catchment. I'll be, there is a paper that's out in Water SA that highlights some of that work. And, there's lots and lots of potential for use in hydrological models for different things, not only satellite rainfall, but evaporation, soil moisture, different types of land cover information, to incorporate stationarity, non-stationarity, dynamic changes in catchments, for example. Obviously, it's going to take a lot of cloud-based computing, supercomputing power, different modeling environments, linking of different models in different ways, etc., to actually incorporate all of those aspects. However, there is a lot of potential that is being shown. Lots and lots of research is required, and I think if we want to really take and embrace the space era and embrace space science and technologies in hydrological analyses, we have to make sure that we're really taking it to the task, and we have to be able to validate our remote sensing products, do our different comparison studies, find more appropriate algorithms and data sets to represent the hydrology of the catchment, and use the in situ information that's available to you. There's no doubt that there needs to be continuous efforts in research. And with South Africa, we've got the South African Earth Observation Network, SEON and FTON, which are NRF-supported research projects, which are looking at keeping up certain monitoring sites and ensuring that there is a continuation of data sets and data availability. And I think this is what's going to help us if we continue this type of work and make sure that we have our invaluable validation data sets available to us. All right, so this is just an example of some of the in-situ systems. They're always going to be around, and they're invaluable, have an invaluable role to play in our work. So that brings me to the end of my presentation. I've left assignment task 1, which is a 1-page summary of any journal article where either satellite-based rainfall, evaporation, soil moisture, or vegetation mapping is used. The article must be less than 5 years old, so anything between 2018 to 2022, and a one-page summary with some sort of critique involved in it would be good. But let's see how you engage with this type of work. So that is the assignment task that I have for you. That's due on Thursday, the 5th of October. There will be on the registrations on the WaterNet online learning platform, there'll be a link that's made available, and there'll be a submission box where you can actually submit these documents through. So that brings me to the end of the presentation. I'm going to stop sharing my screen, and I'm going to make the presentations available on the WaterNet online platform. You'll see it will be available to you in 2 different parts, just so that we can ensure that you have the full presentation. It's quite a large file. That presentation will be uploaded before 3 o'clock this afternoon. And there will also be readings made available to you about networks and the decline of networks, etc. Please, can I ask that you engage with that work, engage with the assignment that's made available to you. And I'm happy to take any questions via the chat, or if anyone wants to just unmute and ask away. So happy to take any questions. Okay, do we have any questions? Sure, the assignment task will be shared as a message on the online learning platform as well. Sorry, did you say kindly share the assignment task as a message? Yes, I will. When your PowerPoint presentation goes up on the learning platform, you also will get the assignment task popping up there as a question to you, and it will be available on your learning platform. So it is going to be available. Are there any questions for me? Any questions? All right, well, if there are no questions, and I'm going to close the session and remind you that the next session is tomorrow. That's quite an interesting session where we
can you hear me?
Hi, yes, I can.
Yes, I was wondering if, anyway, thanks for the great presentation. I was wondering if ever you can be able to share it as well on our emails, the assignment task and the presentation as well.
I'm not sure. I actually don't have your email list, but I could, it's definitely going to be available to everybody that's registered. So if you register, you'll be able to access the site, and you'll be able to download the documents from the site, as well as the task. So once you register on the site, you'll find that the task will come up. There will be email links, which are reminders that will be sent to every person that's registered on that site. So the key to getting all this information is to please register on the site. Dr. Kujinga, are you still with us?
Yes, I'm here. I've shared the registration link with everyone via email, and we are encouraging everyone, as you are saying, to register on the platform, and you have to access all the relevant materials on that platform.
Yes.
Thank you.
All your relevant materials will be made available, so please register onto the site, and that will ensure that once you're registered, you'll find that it will link up to your email, and you will get notifications so that you're able to access the information available to you. Sorry, I see there's a message here. If you're failing to register, can you kindly contact Dr. Kachinga directly? I think you would have had his email address because he would have been in contact with you via email. If you're failing to register, kindly contact Dr. Kachinga via email, and they will be able to help you. I see, can you provide us with access to latest journals, since some are not easily accessible? Unfortunately, access to journals is a completely different issue. Access to journals is dependent on the institution and subscriptions. And yeah, so even we don't have, access to all types of journal articles. Often you'll find that the best route to actually follow is to email the author directly. And you may win with getting a direct copy from the author, even via ResearchGate, if you can't access the journal online via the actual journal site. So that's what I do. If I can't access the journal, I contact the author and, chat with them. So access to latest journals is not something that we can provide to you. It's institutionally based and is limited to people registered with certain institutions. All right. Are there any other questions for me? I will make sure that everything is up before 3 o'clock this afternoon. Actually, within the next hour, we'll start loading. So we just have a few refinements to do, and your work will all be up and available to you. Please join us for the session tomorrow. We start at 10 o'clock on the Google Earth Engine platform. And I think that's an extremely next step. Important next step to what we've been talking about today, is understanding the accessibility of satellite-based products and Google Earth Engine, the cloud computing platform, and its unique abilities to allow users to access data. So please do join us tomorrow in our session. There are no more questions. I'm going to close the session, and I thank you all for joining us. I hope you've enjoyed the session. I've given quite a large overview, and I've tried to select certain things to talk about. Otherwise, I can speak for the whole day. So it's a very important emerging area of research, and I think we really need to embrace it. And I'm so happy to see that there are so many people here interested in embracing these technologies for our hydrological analyses and water resources decision-making and management systems in the future. So thank you, everybody. Thank you for joining. It was really good to have engaged with you.
Maybe before we go, Chetty, we just want to take a group photo. And also, I see another message in the chat, someone failing to register. Please send in an email.
Yes, and also, I've addressed that.
Yeah, and also just to remind everyone that we are meeting on the same link yesterday. So if we could put on our cameras.
Okay, so we're requested to please turn on our cameras just so that we can take a group photo. So it doesn't matter if you have your PJs on.
Okay.
Okay, Dr. Kachinga, are you going to be taking the picture?
Yes, I'm taking.
Okay, that's good.
Okay, that's fine. Thank you very much. See you tomorrow.
Yes, thank you all. I think it was a wonderful turnout, and we look forward to reading those assignments.
And we'll discuss this, but we can make the presentation available online.
Yes, definitely.
once it's available on our link. Thank you very much.
Thank you. Thank you all.
Thank you.